Okay, so this is just another little tutorial to show you some other things that you can do with Spartan, and so make your job a little bit easier doing these lab assignments. So if we click this icon on the left hand corner, new build, so we can build new molecules. And so the assignment for your second computational experiment asks you to do some stuff with rings. So you could either build a ring um, manually, one carbon at a time. So if I'm on this is sp3 carbon, sp2 carbon, sp carbon, so sp3. So then if I click here and click there and there, so now I have 4 carbons. If I want to close this into a ring, then we go down here to the bottom and this button here, make a bond. So then we can click two ends of the two yellows, basically two open vacant valencies on the atom. So if I click here and click there, then now there's a bond between those two carbons. So now that's a cyclobutane. Of course, it's not a very good cyclobutane. So we can quickly clean this structure up. If we go here to build and minimize, then that'll quickly clean the structure up a little bit. So you can see that cyclobutane's puckered. So we could build that way, or if we wanted to, so let's do a new build. We could click this option here, rings, and then you can pick whatever ring you want. So let's do a cyclopentane ring, and then double click here, and now there's a cyclopentane ring, and you can see that it's an envelope shaped. Let's put a cyclohexane ring on there. So now I got 2 molecules on the screen, and they're going to rotate independent or together, but it is possible to move one without the other. So let's see. So I'm on a MacBook. So what I'm doing is I'm holding down the control button and the command button, and then holding down my trackpad with one finger, and then using the other finger on my trackpad to slide things around. So it is possible to move one molecule without the other. If I wanted to move this molecule, if I click that molecule, and then now I can move that molecule wherever I want to move it. So if I'm not holding down command and control, then the 2 molecules move together. If I am holding it down, then I have control of one molecule at a time. Let's see. I'm trying to see if I can rotate around a specific axis. I guess I need to play with it a little bit more to figure out how to do that. Okay, so let's go back to the other one. Let's just do a new molecule. And some other things that you can do. So you can also build by groups at a time. So if I click groups down here, and then you can, whatever you want to do, carbonyl, if you want to add a C double bond O, carboxylic acid, then double click there and it'll add that whole piece for you. So if we want to build the molecule more complex, so let's add a carbon here. And then let's add maybe an alkene. Where's my alkene? We'll need an sp2 hybridized carbon. And so there's my double bond. So if I click there again, then now I've made a carbon-carbon double bond. And if you don't attach anything to the other ends of the yellow sticks, then it'll assume that there's a hydrogen atom there. Okay, so then if we want to clean the structure up again, then we just go to build and minimize, and that'll clean it up real quick for you. And if we want to, so then if you want to go to higher levels of theory for the calculations, you do setup calculations. So again, here equilibrium geometry, if you just pick energy, it's going to calculate the molecule exactly like it is on screen without doing any changes to the molecule. It's not going to tweak any bond lengths. It's not going to change any angles or anything. What we mainly want to be doing is equilibrium geometry. So that's going to allow the program to tweak bond lengths, bond angles, and so forth. And then what you want to do is make sure you have the right, this is what's called level of theory selected. So MMF is molecular mechanics. This is going to be the simplest calculation, and you can do really big molecules with it. PM3 is semi-empirical, so most of your assignment for computational experiment 2 has you using PM3. Hartree-Fock, density functional theory, and molar Placé theory basically uses quantum mechanics to do the calculations, and those calculations are going to take a lot longer to run. They're going to be a little bit more accurate, or in some cases a lot more accurate, but the downside is you can only do smaller molecules unless you have supercomputer capacity, and they're going to take a lot longer to run unless you have supercomputer capacity. And on the A&M Commerce campus, we do have a computer cluster in room 356 in the science building that has a lot of computing power, and we can do very high levels of theories on that computer. But on the student version of the software and on your own personal laptop or desktop, you're probably going to be restricted to lower levels of theory calculations. So if we do a calculation with PM3 and then hit submit, so this particular molecule happens to know its name. Because it's a simple molecule. As you get more complex molecules, the software probably may not know its name. We hit submit, and so you saw up here in the corner it started and then it's already done. So the calculation is already done, and then of course you can look at whatever properties you wanted to look at. You could look at display properties, and then you see the energy of the molecule here, the dipole moment of the molecule. You could display the dipole moment vector if you click that button. So I'm holding down my command button, and that allows me to move the molecule. Or we could have got information here as well if we go display output. And then if we click this output tab here, then this shows you the kind of the raw data output from the calculation. So this is the different cycles it goes through. So in that short amount of time, it did basically 41 different cycles of calculations on this molecule before it optimized and found basically the lowest energy. It tells you the heat of formation. So there's lots of information in here as well. You would just need to take some time to look at this. Maybe you could figure some of it out on your own, or you may need to talk to somebody or myself at some point if this is really interesting to you to know what all of this other information is that the calculation is telling you. But again, so you can find some atomic energy, so what the charge on each of the atoms is if you click that. Okay, so some other things that you can do. Let's turn this off. So let's say I wanted to take this and make an ester out of it instead. So if we bring up the build menu back, edit build. So I click that button there, edit build. Instead of the carboxylic acid, so there's a hydrogen there right now. Let's add something else to it. Let's make an alkyl chain here. So now it's an ester. Okay, let's make this let's make this a cyclic ester. Well, let's put a ring here on this oxygen. So then if I go down here and make bond, and I click these two things, then that attaches those two carbons to each other. And then I'll go build and minimize, and that cleaned the structure up for me. Okay, so let's put a couple of groups onto this cyclopentane ring. So let's put a couple of methyls here. So if I double click there and double click there, then now those two methyl groups are cis to each other. So if you want them trans, you could rebuild the whole molecule, or you can make life simpler, more simple. So you can go here and click that. So that's going to break a bond. Click on the bond that you want to break. So you can see that that bond changed colors. So now that bond is broke. And I'm going to hold down my command and control button on my Mac and my trackpad, and then I can move that out of the way so I can see things better. So let's attach it down here, so then it would be trans. So if I go back over here to this, click this button, make a bond, and click that, Did it work? Yes. And then clean the structure up, minimize it. Then now you can see that that is the trans isomer because this methyl group is on top and this methyl group is on bottom. Okay, so that's a good way to build, to take a molecule that you already have built and then modify the molecule so that you can build something else if you want to. So let's do this again. So let's break this bond, and I'm going to move it out of the way so I can see more clearly, and then let's attach it over here so that the two methyl groups are 1, 2, 3 carbons apart. So I could attach it here, and then it would be cis to this methyl group. Whoops. Or I could attach it here, and then it would be trans to that methyl group. So if I click this again, and then click that, and clean up the structure, build, minimize, then now I have the two methyl groups 1, 2, 3 carbons apart. They're both on top of the ring, or they're both on bottom of the ring, however you want to look at it. But the point is they're on the same side of the ring, so those two methyl groups are cis to each other. Okay, so now you know how to make and break bonds. If I wanted to make a double bond, let's say I wanted a double bond between these two carbons, then just make another bond. So click that again, and click two of these yellow lines, build, minimize, and now there's a double bond you can see between these two carbons. So that carbon has one bond here, and a double bond to that carbon. It's got no yellow sticks hanging off of it, so you know there's no hydrogens on it, so it's only got 3 things attached, which means it must be sp2 hybridized, and it must be double bonded there. If you wanted to make a triple bond, you couldn't make one here between these two carbons because that doesn't have another vacancy that you could attach to. Okay, so let's show you how to do something else. So let's go to a new build, and as you can see down here, it shows you the different molecules that we've studied so far, so you can always go easily back and forth between them. We go to a new build, and let's just build butane. So that has butane built in the anti-conformation, so this would be carbon 1, 2, 3, 4. So if I look down carbon 2, 3, so I'm holding down the Shift and Z button, that allows me to rotate around the Z axis. So that would be a Newman projection where you can see this methyl group is anti to that methyl group. So if we do a calculation on that, setup calculations. So if you're doing a fairly complex molecule, you may typically do an equilibrium geometry on the lowest level of theory possible, submit. So in butane, it's already done. And so that will clean up the structure a little bit. And then if you do setup calculations and now go to a higher level of theory, so it's going to take the output from the MMFF calculation and use that to input into the PM3 calculation, so the structure that you're inputting is a little bit better, and that would make this calculation a little bit faster. So if we do that calculation, and then let's look at the energy here, display properties. So the energy here is negative 121.6, so let's remember that. Negative 121.6 kilojoules per mole for the anti-conformation. Now let's create the Gauss conformation, or let's go for the eclipsed conformation. So what we want to do is change the dihedral. So carbon 1, 2, 3, 4. Right now the dihedral angle is 180 degrees. So this plane between these 3 carbons and this plane between those 3 carbons is 180 degrees apart. If we want to go where this methyl is eclipsed with that, we need to change this dihedral angle around this bond to 0 degrees. So let's go here to geometry, measure dihedral. Let's click the atoms in sequence, 1, 2, 3, 4. Down here it tells you the dihedral angle is 180. Let's make it 0. And so now you can see, now you have the eclipsed conformation. So if I do the calculation on this, set up calculations, and equilibrium geometry, PM3 semi-empirical, and submit. So as you can see, did it stay? It did stay like that. Sometimes it doesn't stay. Sometimes it would, let me see what I did. Okay, I'm surprised that it stayed like that. Usually this is so unstable that it would twist around this bond so that these two are not eclipsed, and they would usually go right to the gauche conformation. What happens if I change this? There we go. So you can see if I did that level of theory, it rotated around that carbon-carbon bond so that now you have the gauche conformation. Well, if we don't want it to rotate, then what we can do, let's go back and change that dihedral. 1, 2, 3, 4. Let's put it back at 0. So it went from 0 to 65 degrees. Put it back at 0. Now it's eclipsed again. And let's do now, let's constrain the dihedral. So click these 4 atoms. And then there's a lock down here. We're going to click that locked. So it's locked at 0 degrees. And then I'm going to go set up calculations again. And then subject to constraints. So we're going to click that. And then hit submit. And so now you can see, you saw it tweak this a little bit, but it did not change the dihedral angle. It's still 0 degrees. It's still eclipsed. So if we display the properties, then we can see the energy now is 0.56 kilojoules per mole. The anti was about negative 121.6. So that's a difference of about 121 kilojoules of energy, where the eclipsed is less stable than the anti. So the more negative that number is, the more stable the conformation is. Okay, so you just have to remember when you do the calculations, if you don't want constraints on, make sure that box is not clicked. Otherwise, it's not going to tweak whatever it is that you constrained. You could constrain bond lengths if you wanted. You could constrain bond angles if you wanted, or you can constrain a dihedral angle if you wanted. So if we wanted to make this gauche, then let's go to geometry, dihedral, 1, 2, 3, 4. Let's make that 60 degrees. And so now we have a gauche conformation. Okay, and I think that's all that I wanted to show you.